Well, Ray, thank you very much for those kind words of introduction. It's hard to compress the full story of gravity. It's such a wonderful and such a complicated story just into the time we have available. Some of you may have noticed there was an error on the website that said the lecture finished at 9:30 a.m. That's been fixed, so sorry about that. But those of you who've bought your breakfast, you're welcome to stay on. I'll continue. Now, a couple of things I'd like you to do. Could you please turn off any apparatus you may have that receives electromagnetic radiation for the duration of the lecture, because I wouldn't like I'm happy for the lecture to be disturbed by gravity waves, but not by electromagnetic waves. Thank you very much. Also, during this lecture, I'm going to forget that I'm talking to a general audience, and I'm going to use the word c. Whenever you hear me say c, I mean actually the speed of light. C for celerity. The speed of light is 3 by 10 to the 8 metres per second, or in other words, about 1 billion kilometres an hour. Fast, but not infinitely fast. C, the speed of light. So, as Ray said, we're celebrating the 100th anniversary of Einstein's general theory of relativity. So I want to take you through where this theory comes from. It's remarkable how little Einstein needed to come up with this extraordinary theory. And this theory is one of the big two theories of physics. The first, the general theory of relativity, explains gravity and the large-scale structure of the universe. The other is, of course, quantum mechanics. Quantum mechanics is the most successful theory for describing the very small. And yet it's a major embarrassment in physics today that these two theories are fundamentally incompatible with each other. And despite the best efforts of the most brilliant minds over the past century, Einstein included, reconciliation of these two theories has not yet been achieved. I'm hoping that someone in my lifetime, perhaps one of our present undergraduates, will finally show what we've been missing all these years and will know the answer of how to reconcile them. So, this theory of general relativity is not just an ordinary theory of physics. It's a theory that has set Einstein among the stars as the all-time, probably the all-time most accomplished physicist, who's made the biggest impact on the way we understand the universe. Time magazine made him Person of the Century. On the cover of Science, celebrating the anniversary. And other people, a couple of physicists, complimented general relativity as perhaps the greatest scientific discovery ever made, the greatest feat of human thinking about nature, said Olivia Newton-John's grandfather. And also the philosopher Bertrand Russell described this as probably the greatest synthetic achievement of the human intellect up to the present time. This is very high praise indeed from distinguished scientists. But let us begin at the beginning, and of course physics begins largely with my hero Galileo. And whenever I get to explain the theories of relativity, starting with Galilean relativity, I'm always excited because this is it's just so great the universe works like this. And I just enjoy seeing the students say their brain hurts after the end of each lecture as they try and come to grips with the extraordinary implications of these theories. Right, so Galilean relativity, introduced by Galileo in 1632 and reaffirmed by Isaac Newton. I'll explain what Galilean relativity is in a moment. That lasted right through until humanity began discovering the properties of electromagnetic phenomena and particularly light. Light didn't seem to fit perfectly with Galileo's relativity. Yet Einstein in 1905 showed us what we were missing. It turns out that the special theory of relativity, which replaced Galilean relativity and brought light into the relativity principles, was already inherent in the laws of electromagnetism that had been worked out in the years before 1905, and there was just a simple thing that everybody had overlooked. It says that the laws of physics don't depend on the speed of the laboratory through the cosmos, and also that the speed of light is the same for all observers. Now, I have to say, when I was sitting in Ray's seat as head of school, I received more correspondence from members of the general public about this second fact, that the speed of light is the same for all observers, because it affronts common sense, as I'll explain. And half of those letters probably came from retired engineers. With all due respect, the letter would typically start, "Dear head of school, I'm a retired engineer and now I've got time to revisit my first love, which was always physics, and I'd like to take issue with the second postulate of special relativity because it's against common sense." The universe doesn't care what your common sense is. And fortunately, Einstein has worked this out, explained it to us, and I prefer a universe that works this way, quite frankly. And then, of course, general relativity, just 10 years later, revolutionised physics, again with the idea of the equivalence principle. So we're not looking at an Einstein that looked like this towards the end of his life. We're looking at an Einstein that looked like this, a young man, not much older, actually, than your children, my children as well. This is the work of a young, fertile mind. So let me start with the first relativity principle, Galilean relativity. Why do we need a relativity principle in the first place? Let me show you this holiday snap. My wife and my daughter on the Field of Miracles in Pisa in January, a cold wintry January of 2010. In the background here we see the Leaning Tower of Pisa. Perfect for doing physics experiments. It's according to legend, but perhaps not according to fact, Galileo threw things off the top of this tower and timed how long they took them to fall. I worked it out, it's about 3.4 seconds to fall from the top of the tower to the bottom. He noticed, first of all, and most important, that everything that he dropped fell and landed on the same spot directly beneath. They fell vertically. He also noticed, correcting for air resistance, that no matter what the thing was made out of, according to legend, or how big it was, how heavy it was, everything fell at a rate of 3.4 seconds. No faster, no slower. Heavy things, light things, they all fell. It took the same time. So the acceleration due to gravity did not depend on the weight of the object. This was a counterintuitive thing because you think a heavier object falls faster than a light object. Not true. Now, let us consider what this means. This is the old geocentric model of the universe. Things fall down because they all fall down to the centre of the universe, which is the Earth. The Earth is fixed immovably, as your instinct tells you, and everything orbits around you, or around the Earth. Teenagers. They grow out of that. But this is not true. It doesn't work. It doesn't explain even the naked eye observations of the way the planets move. Tycho Brahe, more of him later, displaced the planets and put them orbiting around the Sun, but had the Sun still orbiting the Earth, which was fixed in the centre of the cosmos. That doesn't work very well either. And it was Copernicus who put the Sun at the centre of the solar system and put the Earth amongst the 8 planets in orbit around it. So this is a little bit hard to accept because the evidence of our senses is that we are sitting here perfectly at rest. If we were really plunging through the cosmos in orbit around the Sun, which was fixed at the centre of our solar system, then let's re-examine Galileo's experiment from the Leaning Tower of Pisa. He drops the object. It takes 3.4 seconds to fall to reach the ground. But the Earth is orbiting around the Sun, according to Copernicus. And to get from here all the way around the Sun in only 1 year around our orbit, it's a hell of a long way. And we've got to go really fast. 30 kilometres per second is how fast the Earth is travelling in its orbit. So in 3.4 seconds, the Earth moved sideways 101 kilometres. But nevertheless, the object still falls to the bottom of the tower. So this showed Galileo that the laws of physics don't depend on how fast you are travelling. He actually wrote about the idea of doing experiments in a studio fixed to the ground in Padua, where he was a professor of physics for a while. Or the same studio equipped likewise with balls to roll down inclined planes, musical instruments or butterflies flapping through the air, studying those same objects in a studio on a ship travelling at high speed on the open sea. He argued that the observations of the way everything behaved, whether on the fast studio on the ship or on the fixed studio on land, would be exactly the same. To double check that, he interviewed sailors who had fallen from the top of a mast on a ship travelling at high speed on the seas, assuming they survived. And he found that the sailors who fell from these masts always hit the deck at the bottom of the mast. Unfortunately for them, because if it was not for Galilean relativity, as soon as they dropped off the mast, the ship would sail out of the way and they'd land in the sea. But that never happens. They retain the speed of the ship while they're falling. Likewise, this object retains the speed of the Earth even after it's been dropped and is no longer connected to the Earth. So Galileo affirmed this, the Galilean relativity. Newton reaffirmed this, and he made a mistake. He said the universe is governed also by a majestic clockwork where all clocks tick everywhere in majestic synchronisation. But Newton was a genius, and he recognised this was a postulate, an idea that had no testable experimental validity. That's the mark of a genius, to recognise when you're making a hidden assumption. Of course, Einstein abolished this second one in 1905. Now, if it were not for Galilean relativity, life would be very difficult indeed, because here are a few velocity vectors you'd have to worry about in planning the way you moved around. The ground at the latitude of Melbourne travels always towards the east at a speed of 1,000 kilometres an hour, so that we can get from here all the way around our line of latitude in only 24 hours. It's a long way to go. At the equator, the ground moves even faster because the Earth's fatter, and Singapore, where I'll be going on the weekend, has to travel 40,000 kilometres all the way around the equator in just one day. Check the fine print on your discount airline ticket that they include the delta V between Melbourne and Singapore. Some of my friends here have heard these jokes before, but they're still laughing, which is a good sign. Because you wouldn't want to have to hit the ground running at the delta V between Melbourne and Singapore, which is several hundred kilometres an hour. The Sun orbits the centre of our galaxy, as far as we know, at a speed of about 250 kilometres per second, and indeed our galaxy seems to be plunging towards what's called the Great Attractor at a speed of some 7,000 kilometres per second. But fortunately, thanks to Galilean relativity, the laws of physics, as you understand them, don't depend on any of these speeds, and you can go about your business perfectly relaxed without having to worry about them. So let's fast forward now to 1905, Einstein's special relativity. I've explained we first had Galileo, but Galileo didn't know very much about light and electricity and magnetism. Neither did Newton, for that matter. But in 1873, James Clerk Maxwell published his great treatise of electromagnetism that digested everything people knew about the way electricity and magnetism worked, and he wanted to make light an electromagnetic wave, so he took one of the equations and made up a couple of terms in order to derive the speed of light from his equations of electricity and magnetism. Before then, the true nature of light was not understood. Now, if you're a genius, you are allowed to do that. If you're not a genius, don't do it in the exam, for example. It's a bad idea. But if you're a genius, you're allowed to do it, and he was right. His equations then showed that the speed of an electromagnetic wave was c, 1 billion kilometres an hour, and dozens and dozens, thousands of other experiments have shown the validity of this extra term which had been overlooked until then. So electromagnetic waves, fields and waves propagate through a medium. He conjured forth a medium for these, for electricity and magnetism, to carry the signals from place to place in the same way that air carries sound. That turned out to be a mistake, because in 1887 these guys, Michelson and Morley, Michelson was the boss, Morley did the work, failed to detect the motion of the Earth through this all-pervading ether. And in fact, really, this work started with Michael Faraday, went through Maxwell, who did the maths, then Poincaré, who tried to understand what it all meant, until finally Einstein explained what we'd all missed. So let me just explain Michelson-Morley's experiment, because the way they did this was very important for the discovery of the gravitational waves last year. This was Maxwell's idea, that the whole universe was filled with this luminiferous ether, and that carried light from place to place in the same way air carries sound. Now the Earth, in its orbit around the Sun, that was the only velocity vector they knew about in the 1800s. They didn't know about the Earth's orbit around a galaxy because galaxies weren't discovered until my grandfather's time. Before that, there were no galaxies. There was just a universe randomly filled with stars. So this was the velocity vector that Michelson knew about. The Earth's plunging through the ether at 30 kilometres a second. Therefore, there must be this ether wind blowing past the Earth in the same way if you stick your hand out the window of a car at 100 kilometres an hour, even if there's no wind at all, you can feel the air rushing past your hand because of the speed of the car. And so the idea was very simple, actually. You take a beam of light and you send it into the wind. As the light leaves the lamp, the Earth zooms after it at a speed of 30 kilometres a second. You send another beam of light at right angles to the original beam, you flip them back the other way with these mirrors, and then you look at the superimposed waves of light which make an interference pattern. And you do all this on a large block of sandstone which is floating in a bath of mercury, so that it's isolated from vibrations, and then when the time comes you can get Morley to carefully rotate the whole apparatus by 90 degrees and check to see what happens when you interchange the two arms of your interferometer. Because the two beams of light travelling to the right and up and down in this diagram make an interference pattern. And Steve Damon, who's our trusty lecture demo guy, has very kindly set up a Michelson interferometer for us in the lecture theatre. And with a bit of luck, I can get it up on the screen. Yes, okay, so first of all I'll go to this one, that one. Okay, so looking down on the machine, you can just see a source of light shining onto this mirror, bouncing off this mirror, bouncing off this mirror, coming back and being recombined in this telescope. By all means, come down and take a closer look after the lecture. And if we look down the telescope, we see an interference pattern from the light going in the two right-angle directions, recombining the waves and the crests interfere with each other, and we see this pattern. Now, the beauty of this instrument is that this pattern is exquisitely sensitive to the slightest perturbation. And indeed, if I simply breathe into the arm that's going left and right, notice what happens to the pattern. Did it change? Oh, good. Okay. So this instrument was more than sensitive enough to detect the difference in the speed of the light between the into the wind direction or the right angles to the wind direction. So they did this very carefully in the basement of the university. They did this very carefully, it must have caused a bit of grief, on the tops of mountains. They did this very carefully in July. They did this very carefully in January in case there was something bad about the space the Earth was passing through in January. Wait 6 months, try again. But they always got the same result. Michelson wrote in his logbook, it follows that if the ether does slip past the relative velocity, it's less than 1/6 of the Earth's velocity, the velocity of the ether. He was expecting to get 30 kilometres a second, but by looking at the displacement of the interference fringes when you rotate the apparatus, he got something that was barely measurable, consistent with 0. To improve sensitivity, he sent the light bouncing backwards and forwards many times, and it was an extremely nice, brilliant experiment. Now, in order to save the ether, people were very unhappy that you couldn't detect it because the Earth is not fixed at the centre of the cosmos, which this experiment seemed to imply. And so George Fitzgerald, crazy Irish guy, wrote to his good friend Oliver Heaviside, an extremely crazy English guy, and said, Oliver, you're the person who knows the Maxwell equations the best. Is there anything in the Maxwell equations that could have explained this result? Heaviside complained bitterly, locked himself away for a month, and worked out that the Maxwell equations were consistent with the idea that the apparatus could be compressed in the direction of motion by a small amount which explained the null result using the Maxwell equations. And if this compression occurred, here greatly exaggerated, you wouldn't be able to detect the difference in the speed of light in the two right-angle directions. Heaviside was too old when he did this analysis. He didn't understand what he had. We're talking now something like 15 years before Einstein discovered this. Heaviside already had special relativity in his hands, but he didn't understand the dramatic implications of this discovery. So they were right. The Lorentz-Fitzgerald contraction, as it's now called, I am going to call it the Heaviside contraction, because Oliver Heaviside deserves the credit for this, is correct for the wrong reasons. Einstein reaffirmed this and interpreted it differently. This is the compression of the apparatus seen from a stationary observer relative to the Sun as the Earth zooms past. There's no need for this on the Earth because special relativity says the laws of physics don't depend on how fast you're going, therefore you can't use your interferometer inside this lecture theatre to detect the speed at which it travels through the cosmos. Galileo knew that, Einstein knew that, even for electromagnetism. Bern, 1905. Well, this was actually a few years ago when I visited. It hasn't changed very much. This is Einstein Street. If you turn left, this is his apartment, now called the Einstein House, and there you can see Albert looking out the window. If you go up inside, you see this apartment. Einstein was a young man, had a new baby, newly married, Peyton Clark, not even an academic at a university. This is his lounge room. This is the bedroom, and that's about it. That's the whole apartment. But this lace tablecloth, if it could tell stories, this is the lace tablecloth on which Einstein wrote for the first time the laws of special relativity to reconcile electromagnetism with Galileo, and for the first time E equals mc squared derived from sound physical principles. That's me looking out the window. That's me signing the visitor's book. And this is Einstein again now. All the things, this year of miracles, 1905, special relativity introduced June 30, E equals mc squared, just one page introduced in September of the same year. These are the two results which are most important for the remainder of this lecture. We celebrated this 100th anniversary of this extraordinary accomplishment with the Einstein International Year of Physics in 2005. Now, here are the big three results from special relativity which we're going to need to understand general relativity. The first, the laws of physics are the same for everybody. Galileo already told us that, so did Newton. But the second one, the speed of light is the same for everybody. In this lecture theatre, I could set it plunging through space on a spaceship towards the Sun, travelling, say, good speed, half the speed of light. I could let in from that side of the lecture theatre a beam of light. I could watch the beam of light from the Sun pass through the lecture theatre. I could time how long it took to pass through. I know how wide the theatre is, distance over time. I could measure the speed of light. Likewise, I could turn the theatre around and have us zooming away from the Sun at, say, half the speed of light. I could do the same experiment. Let a beam of light in through this side of the theatre, time how long it takes to cross over and exit out the other side, distance over time. Again, I've measured the speed of light. And what's remarkable, no matter what direction I'm going, no matter how fast I go, that beam of light passes through the lecture theatre at the speed of light. Entirely independent of direction. That is the second postulate, and that's why I get so many letters, or used to get so many letters from retired engineers. It defends common sense. Surely, if we're zooming towards the light coming towards us, it should be going faster. Surely, if we're zooming away from the light, we should be leaving it behind, it should be going slower. No! Second postulate, the speed relative to the lecture theatre or the spaceship is the same. And of course, the third big result, the mass-energy equivalent, E equals mc squared. Now, E equals mc squared is a bit of a tricky concept. Everybody knows that it applies to nuclear reactions. You take a nucleus of uranium, uranium-235, the useful isotope, not the useless uranium-238 isotope, the useful one. You can split this in half by hitting it with a neutron. And when it breaks in half, you get two mismatched halves and a couple of neutrons on average left over. And you find that the sum of the parts here is lighter than what you started with by an amount of 0.09%, according to E equals mc squared. And E equals mc squared comes from the idea that momentum is conserved. The laws of physics don't depend on direction. Plus the relativity of simultaneity, events that are simultaneous for me may not be simultaneous for you according to special relativity. This gives us E equals mc squared. It's a direct result of forcing the laws of physics, not forcing, the laws of physics are the same in all reference frames. And I've got a recording of Albert actually describing this in a somewhat quavery voice from the 1930s, which I will just allow Einstein's voice to be heard in the theatre, if this will work. Later we'll hear Einstein's voice in the lecture theatre. Now, what is not widely understood, I discovered when I collaborated with Bernie Hobbs on a special episode of ABC's Catalyst, is that this formula is very simple. It's physics, after all. It's not law, with all due respect if anyone happens to be a lawyer in the audience. There is no fine print on this formula. Here's the fine print. Disclaimer, no disclaimers. E, any sort of energy you like. And indeed, when Bernie explained that on Catalyst one Thursday night, she called me at 6 a.m. the following morning and says, "There's a disaster, you'll have to look at the website, we've got thousands of hostile comments." Because we had the temerity to explain that it also applies to chemistry. So here's my mobile phone, fully charged. It's heavy. The phone has got a lot of energy in the battery, 10,000 joules in fact for my Nexus 5. When the battery goes flat, because I've done too much radiating of voice signals off into the cosmos, the battery is flat, it gets lighter by this many grams according to my calculations. It's very slight because chemical reactions are incredibly feeble. And so the mass change is virtually unmeasurable. And so to allow chemists to make sense of the world, they don't use the mass change in chemical reactions, as is typical inside the lithium batteries in my phone. They take the mass, they multiply it by the speed of light squared, which is a huge number, and use energy instead. If you want to convert mass into energy big time, you've got to use physics, not chemistry. Here's the sun, thermonuclear fusion. 4 million tonnes per second of the sun's mass is being radiated away as heat and light into the solar system. That is a very powerful source of energy. Actually, it's not. It's no more powerful than chemistry. It's just the sun is very big. These nuclear reactions are some of the most feeble that it's possible to have. But we digress. But here is the kicker. E equals mc squared applies to nuclear physics, it applies to chemistry, it also applies to gravity. Now, here are two objects that are far apart. We can extract energy from such a system by allowing the pull of gravity to draw them together until they collide and are stuck. Thereafter, if we want to return them to the initial condition, we've got to pull them apart against gravity. Therefore, this system of two distant objects is heavier by the gravitational potential energy than the same system joined together. This energy has mass. It exerts gravity. Therefore, the mathematics of general relativity is extremely difficult because of this self-referential behaviour of gravity. And only the most brilliant minds in physics can come to terms with this and solve the gravitational field equations. And indeed, it was that sort of energy that was converted into the gravity waves that were detected towards the end of last year. 3 solar masses worth of mass were converted into energy and blasted away through the cosmos in the ripples that finally reached us about 1 billion years after the merger of these 2 black holes. An extraordinary source of energy. No nucleus was harmed in the production of these gravitational waves. It was just a reconfiguration of the gravitational potential energy. So let me now turn to the mystery of gravity. According to legend, Newton was sitting under his apple tree, this is his apple tree, in the garden of his house, and realised that the same force that pulled the apple to the ground also was responsible for holding the moon in its orbit around the Earth. That's an extraordinary insight. And from that, he worked out his law of universal gravitation. I know you shouldn't put equations in public lectures, but hey, this is physics. And this, there's a constant here. There's the product of these 2 masses, say the Earth and the Sun in this example, divided by the square of the distance they are apart, and you can work out how much force there is due to gravity. And later on, in 1798, a very similar law was derived by Augustus Coulomb for a completely different physical system, namely the attraction between the electrons, or he didn't call them electrons in 1798, and the nucleus. Well, he didn't know what a nucleus was in 1798, but nevertheless, this holds the electrons in orbit around the nucleus in an atom. It's an electric force now. This is a gravitational force. Both of these forces are examples of action at a distance. The tendency of one object endowed with a certain property, mass or charge, to reach out through space and exert action on another object similarly endowed some way away. So according to Newton's law of universal gravitation, this lady here and myself are experiencing mutual attraction. We could weigh ourselves, multiply our masses, divide by the distance we are apart, multiply by Newton's constant, and we could work out what the force is between us. It's extremely small from the point of view of physics. But this planet is very heavy, the one we're standing on. It's a lot of mass, and that's pulling me down with quite a considerable force. Not an enormous force, because I can easily break the bond, but then it pulls me back again. But if this was an electrostatic force, I'd be just a thin layer of atomic material smeared across the carpet. Gravity is extremely weak. Not infinitely weak, obviously, because the Earth, with all its matter, pulls us down, but you can do experiments in your own home if you want. Here's the setup. Get a ladder, hang a piece of polystyrene, put 2 masses on the end of it, set up a camera so you don't have to be present and cause air currents that might perturb it, and let it go. And you see with these 2 bulls, they're easily able to realign the beam with the 2 lead fishing weights on it and attract them so that the beam rotates. And there's some idea that from the guy who wrote this, put this up online, very nice. He said, could this have been discovered by the ancient Greeks? Let's use a couple of bits of lead and a couple of blocks of granite, the sort of thing that's lying around in ancient Greece, and a piece of wood instead of a piece of polystyrene foam, and it works perfectly fine. So there's no reason why Newton's universal gravitation couldn't have been discovered 2,500 years ago, but it wasn't. Now, this is the International Space Station, 400 kilometres above us in orbit around the Earth. As we all know, astronauts on the and cosmonauts on the International Space Station are weightless. They're floating about and they don't experience gravity. And indeed, Hollywood is on board with this concept and put this whole movie out called Gravity by mistake, because most of the things that went on in this movie was because of no gravity. So that's what the movie should have been called. And for some reason, the marketing people didn't like that. So, hang on a second. The astronauts aren't that far away. They're only 400 kilometres away. Why aren't they subject to the forces of gravity? Well, let's work that out. Here's the Earth. Imagine building a very tall tower, 400 kilometres tall. Then you climb up the tower. It would take a while, have to take breathing apparatus because it's above the top of the atmosphere. And it's a bit dangerous because you have to duck every 90 minutes when the space station goes past. Now, the gravity on the top of that tower, 400 kilometres above the surface of a planet with a radius of 6,350 kilometres, work it out by Newton's universal gravitation, turns out to be almost the same, to within 10% or so, of what we're experiencing right here. So if we were in a lecture theatre on the top of the tower, suitably supplied with oxygen, you would hardly notice the difference to what you're experiencing now. So those astronauts are feeling plenty of gravity, and yet they're weightless. Why? Well, the answer, like the sailor falling off the mast on a ship at high speed, is weightless because they are falling. They are falling towards the Earth, but the Earth keeps curving out of the way, so they keep missing. And they're falling around the Earth eternally in this orbit. They're not weightless because there's no gravity. The gravity is almost the same as down here. They're weightless because they are falling. So this is an extraordinary thing. You can eliminate gravity just by falling. That seems bizarre. Let's check it out experimentally in case there's something funny about the space station. Here is my lecture accelerometer. If I now accelerate to the right and then stop, you can see my acceleration vectors. Now, let me throw this into the air. If I throw this into the air, it'll accelerate downwards at a rate of 9.8 metres per second squared, the same as what Galileo measured on the top of the Leaning Tower of Pisa, and the same as what you can calculate with Newton's law. Watch carefully what happens when I throw it. Did you see that? Or rather, did you not see that? All the lights go off. While it's falling, it is weightless. It cannot measure acceleration. It cannot measure gravity, like the astronauts. It is weightless. If I put it down on the bench, according to the accelerometer, we are accelerating upwards with an acceleration of 9.8 metres per second squared. You know that because you can feel the seat pushing on you, pushing you upwards. In the same way, if you're sitting on an aircraft, it's lightly loaded, and it accelerates down the runway, you can feel the seat pushing you to accelerate you. The accelerometer cannot tell the difference between an acceleration or the pull of gravity. Likewise, the astronauts are falling downwards with an acceleration of 8.71 metres per second squared, which exactly counters the pull of gravity at that height of the orbit. Now, of course, when you're in space, humans don't like it very much because they're designed for gravity. And so here is a 1969 design of a 2001 International Space Station from the magnificent science fiction movie 2001: A Space Odyssey. When I look at this and I look at the picture of the real space station, I sometimes feel I've gone into the wrong future. Anyway, this is rotating. This is rotating at high speed so that the centripetal force gives the sensation of gravity back to the astronauts who aren't feeling gravity because they would otherwise be falling. So this is the second result. You can restore gravity by accelerating. Let me show you a demonstration. I haven't got time to show you that one. Before I do, I need to do one more demo. Steve, do I need to turn the lights on for this, do you think, or will it be good enough? Is the camera going to be good enough to see this? That one. And I have to go there. Oh, great. Now, what I've got here is a tube full of air. And at one end of the tube, is that maybe, yeah, would you mind, Steve? Yeah. I'll do this one first. In this tube there is air, and there is a feather, and there is a little cube, which I think you can see there. The little red cube and a little green feather. And because the tube is full of air, the little cube falls a lot faster than the feather does. The feather takes forever to fall down the tube through the thick air. But what I can do with this is suck the air out. I can suck the air out. Doesn't look like the camera sees the little red cube very well. Sees the feather just great. I think that's just fluorescing at the wrong wavelength. Okay, so after a few moments, the vacuum pump has sucked the air out. And at least those of you who are down the front and can see the little red cube will be able to see what happens next. If I now invert this, both the feather and the little red cube fall more or less at the same rate. The air's leaking quickly back in. So that's a remarkable result, that the fall doesn't depend on whether you're a feather or a little red cube made of lead or something. So let us now consider then what's going on here from a mathematical and physical point of view. Here is an object falling subject to the pull of gravity near the Earth. We can use Newton's law of universal gravitation to work out the acceleration that Spider-Man is experiencing here. It's just the gravitational constant times the mass of Spider-Man times the mass of the Earth divided by the radius of the Earth squared. The action at a distance. Something is going on in the gap here that causes the mass of the Earth to reach out and pull Spider-Man down. And the reverse. Spider-Man is reaching out and pulling the Earth up, but the Earth is very big, it doesn't move very much. So when I jump, I've pulled the Earth up a little bit, but not enough to affect its orbit, I'm pleased to say. Now, Newton also said from the second law that the force you apply on an object causes it to move with an acceleration that's proportional to its inertial mass. This is the property of inertia. This is something different to gravity. Gravity is the property of an object that causes it to exert action at a distance. Inertia is the property of the object that causes it to resist being set in motion. And you can see here, we can take the F from Newton, plug it in over here, into this equation also from Newton. We get this equation. We can cancel off the mass of Spider-Man. We end up with constants that just depend on the properties of the Earth, and when we plug them in, we get 9.8 metres per second squared, the acceleration of those objects in the vacuum pipe. And because we cancelled Spider-Man's gravitational attributes with Spider-Man's inertial attributes, it's the same for all objects. Newton knew this, and he knew these were two entirely different physical phenomena, but he never figured out why this could be cancelled here. It was just a staggering coincidence. And this has been repeated over and over again, these sorts of tests, and are accurate to 1 part in 10 to the 12 or better. The inertial mass and the gravitational mass are the same for all objects. No wonder whenever you see a painting of Newton, he always looks unhappy. People say it's because he had false teeth or he had arsenic poisoning. No! He's saying, why are these two the same and why can I cancel them? Now, it's a strange thing. We're going to get ready to do the monkey, Steve. Can you get the monkey charged up? It's another strange thing that this is a pendulum with a mass on the end of it. And when I let this go and let it dangle, it's hanging down. Well, obviously. But no, not obviously. Because here at the latitude of Melbourne, remember the ground is moving in a circle at a speed of over 1,000 kilometres an hour. So if this wasn't being pulled down by gravity, it would be flung off into space. And indeed, if there was a discrepancy between the inertial mass and the gravitational mass, it would hang, say, out like this. A partial tendency to be thrown off, but still being pulled down by gravity. If there was no gravitational mass at all, it would hang pointing straight up because it's trying to be thrown off into space. And so by comparing the distance down for all sorts of different objects, you find it's always the same, no matter what they're made out of. And this is also a remarkable thing. Okay, Steve, while I turn the lights on, let's do the monkey. Here's a very common physical scenario. There's a monkey in a tree over here. And over here there is a hunter equipped with a bazooka.
Put it on the camera.
You can put it on the camera. Now, this monkey doesn't like being bazookaed. So the monkey has snuck in at night and fitted a photocell across the muzzle of the bazooka. And the monkey has also been fitted with an electromagnet in the top of its head, connected via a circuit back to the photocell in the bazooka. As a safety precaution, when the projectile emerges from the bazooka, it interrupts the photocell, turns off the electromagnet, and the monkey drops harmlessly out of harm's way. Let's see if the physical reasoning here is correct. Okay, go for it. Oh, bad idea. The monkey still got hit by the projectile. Why? Both the monkey falls, and the instant the projectile comes out of the bazooka, it also falls. So despite the velocity vector heading up this way, both the monkey and the projectile fell at the same rate, and the trajectory of the projectile intersected with the monkey as it always does. Another example of everything falling at the same rate. So this equivalence between acceleration and gravity led to Einstein's general relativity, the equivalence principle. A really simple idea. Let me digress for a moment. When Einstein was very young, only I think 12 years old, one of his uncles gave him a book on geometry. And Einstein was enraptured with this book. So beautiful in its purity, so austere in the small number of assumptions you need to determine a whole lot of Euclidean geometrical handy stuff. He called it the Holy Geometry Booklet. We don't know which one it is, but it looks something like this. So he was always very interested in geometry, and that's going to be important in what follows. In 1915, he said, let's just recognise what the universe is telling us. We'll assume complete physical equivalence of a gravitational field and the corresponding acceleration of the reference frame. This assumption extends the principle of special relativity to the case of uniformly accelerated motion of the reference frame. 4 extraordinarily thorough papers that used his geometrical understanding and that of his colleagues to write down a set of equations which are still as accurate today with all the things we've done to them over the intervening 100 years, and they've stood the test of time. This is what the equivalence principle tells us. We can be in a lecture theatre on the Earth. Things fall down. We could equivalently be in deep space on a rocket ship which is accelerating at 9.8 metres per second squared. Everything likewise will fall down. The laws of physics are the same in both scenarios, whether it's gravity or whether it's acceleration. Likewise, I could be in a lecture theatre falling towards the surface of the Earth, and in those few moments before the lecture theatre intersects with the surface of the Earth, everything is floating around. Yes, that's not an optical illusion, I am floating there. Or I could be out in deep space, far away from any gravity, and again, everything would be floating. The physics in these two laboratories is identical. So let's put this to work. Here's a very simple physical scenario. A rotating disk with an observer on the disk and an observer on the ground. I've got one. Here it is. Oh, here it is. Get this on. And I need to turn this on. Sorry, it's number 3 or number 2?
It's number 3.
Number 3. Oh, there we are. There we are. That's perfect. Perfect. So I can set this disk spinning, and I've put a number of vehicles on the disk, a number of matchbox cars. Look carefully at what happens from the vantage point of this camera, which is rotating with the disk as I set it in motion. Nothing. So let's go faster. Well, no surprises there. As a result of the spin, all the vehicles are deflected and they all crash into the walls of the device. It's so nice. I'll just do that one last time to show that it works even if they go backwards. Here we go. So what that looks like on your camera, like some mysterious force has suddenly appeared and deflected all the cars to the edge of the disk. So we can use the equivalence principle to understand what this tells us about gravity. So here's an observer on the ground that lays down 12 1-metre rulers around the edge of the disk. It's a lot bigger than the one I've got here. Calculates the circumference. It's 12 times 1 metre, and that equals 2 pi times the radius in the traditional way. But let's look at these rulers from the vantage point of the observer on the disk. The observer on the disk, like this camera, is at rest and subject to an acceleration that's pushing them against the walls of the cylinder like the cars are now. And the observer watches these rulers go flipping past at high speed. Now, by the Lorentz contraction, they all shrink as they zip past. And she sees 12 of them flip past, but they're all shrunken compared to her ruler. And so therefore she deduces 12 rulers that are shrunk by this factor, the circumference of my disk is less than 12 metres. The circumference of this circle is less than 2 pi r for an accelerated, for the spinning disk. But we can map that straight across and say by the equivalence principle that also applies to gravity. So in other words, in flat space, in the absence of gravity, circumferences of circles are 2 pi r, but in curved space, like this shape, the circumference of that circle is less than 2 pi r. That is the geometry of the space inhabited by people on this disk. It's not Euclidean. It's like drawing the circumference of the equator, which is 40,000 kilometres, which is a lot less than 2 pi times the radius of the Earth, because it droops around. So, if we apply the equivalence principle, gravity is geometry. And the curvature is different to what it's like on this disk, because here gravity kind of pulls everything out, but on a planet or a star, gravity pulls everything down. And so this is the curvature with a few lines of Fortran code, Ken. You can't do that with C, I'm sure, with a few lines. There's the sun. This is the two-dimensional representation of the curvature of space. Notice there's convex curvature if you go in this direction. There's concave curvature if you go in that direction. The circumference of circles here are greater than 2 pi r. You can test this. Einstein said, it's hard to believe, but this is true. Imagine you look at these two stars where the light from those two stars reaches us, scraping past the sun. When we look back along the line of sight, if space is really curved like this, the geometrical distortions, then if we sight back along where the light appears to be coming from, we'll see the stars over here, not where they really are. Now, of course, you can't do this unless the moon is in the way, blocking out the sun. So You then wait until the sun goes somewhere else and you take a photograph of the two stars, which are now undistorted, and you compare the positions to see if this equivalence principle can be true. So in 1919, after the First World War finished, Arthur Eddington went to Africa where there was this total eclipse of the sun and photographed a couple of stars during the eclipse. He then waited until the sun was out of the way. A few months later, photographed them again, found a discrepancy that agreed exactly with Einstein's theory. Even modern analysis of his data from his plates, photographic plates which still exist, confirm this conclusion. Einstein immediately became famous. The New York Times had a headline, "Light all askew in the heavens, Einstein's theory triumphs." The paper reassured its readers that only 12 wise men would be able to understand it. That's because all the women already understood it, I guess, in those years. But those data were already known to be dodgy, and there was another eclipse in Australia in 1922, just 3 years later, and people knew they had to get better data. So there was an Australian expedition went up to observe the eclipse from Melbourne on the east coast, and there was an American expedition that observed from the west coast. And they attended a gigantic dinner at the Royal Society building down there in Rathdown Street before they headed off, presumably by ship, to make the observation, and excellent data were obtained by both expeditions. This moved the Vice-Chancellor of this Chancellor of this university to team up with the University of Sydney Chancellor and the University of Adelaide to write a letter to Einstein, here's a copy of it, inviting him to come here and give us some lectures. We'd welcome the opportunity of hearing from your own lips some account of your theories. They offered him £100 and all expenses. Unfortunately, Einstein never came to Melbourne and lectured to us, too bad. Finally, the mystery of the planet Mercury. This is a snapshot of our solar system taken from outside by the Voyager spacecraft, which left our solar system some decades ago, and this was the last series of photographs of the planets of the solar system it took before they turned the cameras off forever as it plunged out into interstellar space. It's humbling to look at this, how insignificant our planet appears, hardly visible against the glare of the sun from this enormous distance. Kepler worked out how the planets orbited. He worked out some laws which govern the orbits, the regular aspects of our planets in our solar system. This is his house in Prague. It's now a museum. This is the door under which letters from Galileo would be slipped periodically, driving Kepler nuts because Galileo was finding lots of new things and Kepler wanted to test his theories. This is the street off which the alleyway leads to his house. This is the Charles Bridge in Prague. In the nearby cathedral, Tycho Brahe is buried. Now, using Kepler's laws, people applied them very carefully to accurate observations of the planets in our solar system and discovered that Uranus didn't follow Newton's laws perfectly. And over the years, people predicted that the discrepancies in the orbit must be due to another planet that was undiscovered until 1846, namely Neptune. Those of you who were at my lecture in 2009 will remember that, of course, Galileo saw Neptune first, and I speculated whether he knew he'd seen a new planet, the first new planet discovered by humanity since deep antiquity. And if you bring up the Wikipedia article, I still get a mention. That was just a humorous idea at the end of a July lecture, now enshrined in Wikipedia. But here's the table of data for our solar system. Kepler's laws are followed beautifully. Newtonian gravity, beautiful. Except for Mercury, the most elliptical orbit, the smallest radius closest to the Sun, and the biggest error. We're looking here at a breakdown of Newtonian gravity. People worried about this. They could calculate to very high precision the orbit of Mercury perturbed by the other planets, the known planets of the solar system, and no matter how carefully they did the calculation, and celestial mechanics is extremely accurate, there was still this discrepancy that could not be accounted for by the known planets. So it must be due to an unknown planet, just like Uranus was perturbed by the hitherto unknown planet Neptune, and it was called Vulcan. And Vulcan must orbit between Mercury and the Sun. So people looked for it, following the predictions of the theorists. They were looking for transit. This is the transit of Venus in June of 2012. A good way of spotting planets between us and the Sun. Mercury is also possible to be observed with this method, but it's very hard to distinguish between a planet and sunspots. And unfortunately, despite a lot of announcements with great fanfare, Vulcan has been found exactly where the theorists said it would be, but it never came back on another orbit. And it was only sunspots, not a planet, because there is no planet Vulcan. Mercury orbits not in flat Euclidean space, but in highly distorted space caused by the Sun's gravity. So, in conclusion, Einstein's theory has withstood everything we have thrown at it over the century since it was first written down. And the topic of the next lecture, which I will just conclude with, is now the discovery with two gigantic Michelson interferometers, one here in Washington, one here in Louisiana, operating in coincidence mode, that detected the changes of geometry, not the radiation, the changes of geometry due to the coalescing of two black holes more than 1 billion light years away. And it's a truly, truly remarkable discovery. We knew it was coming, but to actually hear the signal and see the results is just, I'm just so excited about this, because this is a window on the sky not from our familiar electromagnetic radiation. It's a new window on the sky in ripples in geometry. And so now there's just a little bit of unfinished business. One by one, the forces of nature have succumbed to the power of quantum mechanics. Professor Volkas doesn't use simple-minded diagrams like this. He uses Feynman diagrams, which explain the quantum mechanical attributes of the forces, the action at a distance between these two particles. And these have been worked out and have enormous predictive power. The Higgs boson ultimately came from treating the quantum mechanical attributes of the forces of nature. But one force remains aloof. Gravity does not seem to be a quantum mechanical attribute. It's a geometrical attribute, as I've explained. So this is unfinished business. But the Gravity Wave Observatory, 406 years after Galileo's optical telescope, has opened a new window on the sky from changes of geometry. So the last word belongs to Galileo. I think I finished my 2009 lecture in the same way. Philosophy is written in this great book, by which I mean the universe, which stands always open to our view. Anyone can look into the sky, maybe not with a gravity wave observer, but with a telescope. But it cannot be understood unless one learns how to comprehend the language and interpret the symbols in which it is written. And the symbols are triangles, circles, and other geometrical figures. Galileo is anticipating general relativity here, without which it's not humanly possible to comprehend even one word of it. Without these, one wanders in a dark labyrinth. Ladies and gentlemen, thank you for your attention.
Exciting tour through the world of Einstein and gravity and gravity waves. Are you happy to take a couple of minutes of questions?
Yes, I know I did go very fast to try and do some time dilation there.
Yeah, it didn't work. Actually, I reserve the right to ask the first question.
Oh, certainly.
You have some apparatus here which you didn't actually use. Do you care to...
Well, yes, this is... someone might have picked me up. I calculated that I weigh 110 grams less in Singapore than I do here in Melbourne because of the centripetal force effect. And in this model of the Earth, you can see as I speed it up, you can see the enormous forces at the equator would throw anything off. If the Earth had a day of just a few minutes long, we'd all be flung off into space. But instead, the difference between Melbourne and Singapore, assuming a perfectly spherical Earth, in my weight is only 110 grams. Now, those of you who know me well know that when I land in Singapore, I go straight round to Sammy's curry house and order the banquet, and that soon takes care of that 110 grams right there. Yeah.
Where is Sammy's curry house?
It's just next to the Botanical Gardens, yeah.
All right, now we'll take questions, yes.
Thank you, Professor Organizer. I appreciate that. I catch a lot of knowledge. I have some two questions. What different special relativity by general relativity in multi-universe, if we believe multi-universe, if we understand gravity, how we understand universe, what is gravity and how work in practical, especially in the laboratory?
Okay, so first of all, as I concluded there is no quantum mechanical theory of gravity yet. Maybe there will, maybe humans aren't smart enough to work it out. Maybe, that would be a depressing thought, because we do seem to be, generally speaking, notwithstanding recent events, pretty smart. But the universe is probably smarter than us, and therefore there are no multi-universes from the point of view of gravity, because that requires quantum mechanics. So I don't think it's going to be complicated, but all the concepts of quantum mechanics, as far as we know today, do not apply to gravitational phenomena. It's purely classical. As I tell my first year students, when I teach classical physics, you will not see Planck's constant in any of these lecture slides, because that's a constant to do with quantum mechanics. In gravity, there is no Planck's constant.
Just a quote I'd like to read. It's not a question.
Oh.
George Bernard Shaw, in 1930, when he was introducing Einstein, the time we made a universe that lasted 1400 years, Newton made one that lasted 300 years. I wonder how long Einstein's universe will last.
Forever.
Here's the prediction we'll try to verify that. Other questions?
Is C constant if you're going faster than C?
Well, that's a very good question. I have to compliment you on your English grammar, because there are no grammatical errors in your question whatsoever. The structure of the English language allows you to ask such a question. However, the universe does not. That's a very common question. What happens if you go faster than the speed of light? Let me give you a simple answer. I showed the Heaviside contraction. The correct result derived from electromagnetism that Einstein also put forward in his paper in 1905. Moving objects contract in their direction of motion by that factor. If you look at the equation, you see that as a moving object approaches the speed of light, the contraction gets ever smaller, until at the speed of light it's contracted to zero. Therefore, if I was to hop into a fast spaceship powered by some engine of unknown properties but enormous power, and I accelerated off until I started to approach the speed of light relative to the universe, of course I'm sitting in my spaceship perfectly relaxed, maybe having a glass of Shiraz, looking out the window at this very small universe going past, getting ever smaller. And eventually the size of the universe from my reference frame goes to zero. Therefore, I am everywhere. There's nowhere else to go. The universe has gone. It's just a dimensionless point, and that's the size of the universe seen by a photon. So you can't go faster than the speed of light because there's nowhere to go.
Other questions?
Could you just outline in brief for what reason general relativity breaks down at the singularity?
Yeah, well, that's a very insightful question. The question is, for what reason does general relativity break down at the singularity? That's a very good question. So if I can just have camera number 4, because that gives me a chance to do one last lecture demonstration. I understand if you have to go, you've got to go, but let me just do this one last demonstration. Camera number 4. Yes, Steve. I think I've got enough expertise to do this. Okay, so... oh, yeah. Whoop, 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 whoop. Okay. Here is my physical model of a heavy object distorting space-time. Thank you. And here is Mercury orbiting, just escape velocity, orbiting that heavy object because of geometry, which is what we call gravity. Now, imagine that object was really heavy and it distorted that sheet. And it was so heavy, it distorted that sheet until it dropped down to infinity. The walls of this curvature became parallel. The object has gone. It's infinitely far away. The gravity is still there as long as you don't get too close to it. You can still orbit it out here. But the object has gone down into its own gravitational field. That is the formation of a singularity, where the gravity is so strong, there is no longer a force left. We've only got 4 to choose in our list. There is no longer a force strong enough to hold the object up against the remorseless inward pull of gravity, because gravity is always attractive. And once you overwhelm the strong nuclear force with gravity, down it goes. And that's why it's called a singularity, because if there's no force strong enough to sustain the diameter anymore, the Earth, it's the strength of rocks, the Sun, it's gas pressure, a neutron star, it's the strong nuclear force, a black hole, we've run out of forces. But quantum mechanics doesn't allow singularities. When you try and put things close together, like when you drop an electron onto a nucleus, it's pulled in by the Coulomb force, and the electron should go zooming in and crash into the nucleus and blow up. But obviously we're here, atoms don't blow up, despite the fact they've got electrons being pulled down tightly against the nucleus, because the electron is a quantum particle. And when it gets close to the nucleus, its wave-like quantum attributes become evident, and it can't get any closer than the minimum number of wavelengths the electron can have, and that's where it goes into orbit. It doesn't collapse any deeper. Presumably something like that happens with gravity. Once the mass gets so small that the quantum attributes of the matter, or whatever's, it's not matter anymore, it's just geometry, will take over and prevent the singularity from forming. But as yet, we don't have a good understanding of how that works. So from now on, we'll continue to talk about singularities, even though in my other lectures I say, well, of course, quantum mechanics, you can't have a singularity, let's calculate the energy spectrum of the hydrogen atom.
Okay, we'll have one more question from up the back here.
Professor Jamieson, the exact equivalence of inertial mass and gravitational mass, can it possibly be a coincidence, because inertial mass is utterly insensitive to the gravitational field? Do we have an explanation of why that is yet?
Well, this is the great mystery that Newton grappled with. It's not strictly independent because, of course, the inertial mass also depends on the gravitational potential energy. So it's a very complicated thing, actually, when you work it out following Einstein's guidance from 1915. It's, why does the universe work like that? Blowed if I know, but I'm glad it does. Because it's really interesting. And one day we'll figure it out. Well, not me personally, but the students in my first year lectures, hopefully. Right. Please hurry up.
I think we better stop the questions there. Before we thank David, we should thank Steve Damon, who's the technician responsible for setting up.
Yes, thank you, Steve.
And now let's thank David once again for a wonderful lecture.
Thank you.